So welcome all to week 9 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR IIT Bombay. So the topics that I plan to cover is going to be related to optimization in general. Okay. So the instructor in the course has talked about unconstrained optimization. I'll also talk about it. Okay. Then he has talked about KKT conditions for constraint optimization. And he has also covered this steepest descent, or a common name for which is gradient descent method. Okay. Okay. So I think this topic was covered in the course, but I want to give some more insight about this particular topic, steepest descent or gradient descent method, from perspective of how do you apply it to some machine learning algorithm. Okay. So I think mathematically this topic has been covered, but I'll talk about it from implementation point of view. Okay. And then we will look at some other methods like Newton's method. Okay. Or penalty function method. Although, if you look at the optimization, like optimization as a subject, it's a broad area. For example, in our department, if you look at the name IUR, OR part, operation research part, we mainly deal with optimization. Okay, the department mainly deals with optimization. It's a broad area on its own. But if you look at what kind of methods are applied for machine learning application, most of the place you will see gradient descent or its variant being applied. Okay. Like if you look at optimization as an area on its own, there are many methods, but the ones that are being applied in machine learning mostly are gradient descent and its variants. At least when you apply it for some application, if you are not into research, this is what you're going to use. Okay, so gradient descent and its variants. Okay, okay. So just a recap from last time. So in general, how an optimization problem looks like is something like this. So let's call this as problem P. This would look something like maximize some f of x, or it can be minimize or maximize some f of x subject to some constraints. Okay. And those constraints would be some gi of x is, let's say, less than equal to 0, something of this form, or hi of x some is equal to 0. Okay. And something, yeah, these are the kind of constraints that you can encounter. So this in general is called as a optimization problem. Okay. So you want to minimize this function f of x such that your x also satisfies all these conditions that are mentioned over here. Okay. So satisfying all the constraints, you want to look at the minimum or maximum value of f of x. That's the whole aim. Okay. So first class of optimization problem that you encounter, uh, if you go by approach of the way the instructor has taught, so first class would be unconstrained optimization. Okay, these are slightly easier to solve. Okay, unconstrained optimization do not have any constraint. Okay, so you are only given with some f of x and you want to either minimize this or maximize this. Okay, so if you have a function that you want to minimize or maximize without any constraint, you might recall what you did in your class 11th or 12th. Let's say you are given with f of x is equal to, let's say, 3x squared plus 2x, let's say, and you are asked to minimize this function. What you used to do is, first of all, you used to do f dash x is equal to 0 to obtain stationary points. Okay. So in this case, it would be cx plus 2 is equal to 0. or x is equal to minus 1 by 3, right? And then what you did is, then you calculated f double dash x, okay? And based on sign of your f double dash x, okay, as it is greater than 0, you can say that this is local minima, right? Or yeah, this is what you did in class 12. Now what we are dealing with is a function of more than one variable. So if you look at a general machine learning model, the feature that you input is generally more than one dimensional. Okay, so you have some feature vector having x1, x2, xn, right? And you have some loss function associated with your model. So why are we studying optimization is that you want to minimize this loss function, right? You want to minimize this loss function. Okay. So we will do similar thing as we did in class 11th or 12th, but now because your function is multivariate, this f dash x and f double dash x will have a new cloth, or you can say a new form. So f dash x is replaced by gradient of f at the point x. So in order to find the stationary point, you should have gradient of f at that particular point is 0. Okay. And what is something similar to your f double dash x? Okay. Now your f double dash x is replaced by Hessian. Okay. Now just recall that your f double dash x was a single value that you were able to compare with 0, whether it's greater than 0 or less than 0. But your Hessian matrix over here is no more a single value, but it's a matrix, right? So you can't actually compare whether a matrix is greater than 0 or less than 0. So something, a generalized version of greater than 0, less than 0 that you come up with is semi-definiteness. Okay. If your Hessian matrix is positive semi-definite at that point, then your function has local minima at that point. Okay. If it is negative semi-definite, then it's maxima. And if it is indefinite, then it's a saddle point or you can't comment, right? Then it's a saddle point or you can't say anything about. Okay. Right. Okay. So this is what you will do. Okay. So if you have to find a minimum point, first of all, you will solve for delta f of x is equal to 0 to find out all stationary points, right? And then you will apply the condition that Hessian is positive semi-definite. Okay. So together these two conditions will give you whether a point is local minima or not. Okay. So in the instruction given by the professor in the course, you might have heard that he says that the second order condition is a necessary condition, and if you mix it with this condition that x bar is a stationary point, then only it becomes a sufficient condition. Okay, so don't get confused by this. It's intuitive, because let's say if you had a function like f of x is equal to 3x square plus 2, the example that we saw, you take any point, at any point, f double dash x is always 6, which is greater than 0, right? But any point is not a local minima, right? So first you need to solve, check whether a point is stationary point or not, right? And then if you merge it with this condition that your f double dash x is greater than 0 or less than 0, then you were able to infer whether it's a local minima or a local maxima. So that's why this condition is also necessary in order to make it a sufficient condition, is that your x dash is a stationary point, and then you have to check your Hessian is positive semi-definite or not. So you need to satisfy both these conditions in order to guarantee that your point x is a local minimum. Okay. This is one thing. Okay. So, okay, before going into this KKT conditions and all, I'll straight away introduce steepest gradient method or a steepest descent method or a gradient descent method. I think it's a important method if you talk with respect to machine learning. Then we will go to all these other methods which I don't think are that important. At least from machine, they are very important. Like if you talk about optimization community, but from machine learning perspective, these are the more important ones. Okay. Okay. So steepest descent or gradient descent is the same name for both the methods. So it's the same name for, uh, like it's a different name for same method. So you can either call it steepest descent or you can call it gradient descent. Okay. Gradient descent I think is a more common name across machine learning community, and steepest descent is hence a less used nomenclature. Okay. So idea is very simple. Okay, when we talked about gradient, we talked about a property of gradient that if you calculate gradient of f at some point, right, this direction is the direction in which your function increases at maximum speed. Function increases at maximum speed. Okay. And I think I also mentioned in the last class that if you take negative of this quantity, that is, if you take negative of your gradient, okay, this is the direction in which your function decreases with maximum speed, right? So the idea behind using steepest descent method is, let's say I begin at some arbitrary point x naught. Okay, what I do is I'll calculate negative of gradient at this point x naught. So standing at x naught, if I move in this particular direction, let's call this as d. Okay, if I move in direction d, then I'm decreasing my function at a maximum speed. So what I suggested, let's move in this direction. Okay, so if I'm standing at some point x naught, let's move in this direction d. Okay, so what I'll do is my x1 would be x naught minus gradient of f of x naught. But how much should I move in this direction? That I don't know. Okay, so let's say I move lambda unit in that particular direction. Okay, so your gradient descent is just given by x1 is equal to x naught minus lambda times gradient of f of x naught. Okay, and this method is known as gradient descent method. You keep repeating this thing till the time you converge. Okay. Okay. So let's say here I had an example where you are optimizing some linear regression function. Okay. So you are given with some data point of form x comma y, right? Where x is a single value and y is also some single value, and you approximate your f by let's say ax plus b, right? Then the loss function between f of x and y is given by y minus f of x whole square. Okay, so you want to minimize this loss, right? So this is the update step that is given. So your x vector now is of a comma b, right? So if this is your a1, this is your a naught, then a1 is given by a naught minus some alpha times del j by del alpha. So this alpha and lambda are same, the lambda that we talked about few minutes ago. And similarly, your b can also be updated. Okay, so this is how your gradient descent method works. Okay, I'll give you an intuition on 2 dimension. So let's say you arbitrarily start at some point. Okay, this is the point. Okay, from here, let's say you started at point minus 7.5. You have only two paths to go. Either you can go in the left direction or you can go in the right direction, right? You only have two choices. So in which direction should you go? In the direction in which your function is increasing or in the direction in which your function is decreasing? obviously you will go in the direction in which your function is decreasing because you want to minimize your loss. Okay. So let's say in this direction, you move from here to here. Okay. So on the plot, you will move from here to here. Okay. Then again, you look at this point whether your function is increasing or decreasing, and you move by some margin. Let's say you reach here. Then again, you check whether it's increasing or decreasing. You reach something here, then here, and you finally converge to this point. So this is the idea behind gradient descent method in multi-dimension setup also. So you keep moving in the direction in which your function is decreasing, and eventually hope that you reach a point where you have converged. Okay. Okay. So before choosing alpha, there is one thing that I want to mention. So one thing is clear from our discussion is that this steepest gradient method or the steepest descent method or the gradient descent method is an iterative scheme, right? So from x node, you go to x1, you go to x2, and so on, right? So the question is, when do you stop? So this is an important question, right? So should you keep doing it till infinity or when should you stop? Okay. So when you are implementing, the first check that you can do is if the gradient at some of, let's say some xk turns out to be 0, okay, then because your gradient is 0, you can't further update your x, right? You will keep getting same x from here on. Okay. So in this condition, you should stop. Okay, so your gradient has become very small, or many times it won't actually go to 0. So you can have a tolerance that if your gradient at some point has become, let's say, less than some 10 to the power minus 5 or 10 to the power minus 6, or it has become very small, then also you can stop. Okay. This is one way you can decide when to stop. Another way is if xk minus xk minus 1. So the update that you're making, this update in x is very small. Okay. So rather than 10 to the power minus 5, I'll write some epsilon. So this epsilon is very small value. If it so and it's up to you, like when do you want to stop? What's the choice of epsilon that you want to make? If it has become lesser than that, then you should stop. Okay. There is one more method that you can use to stop. Rather than looking at your values, you look at value of function. Okay. If the value of function is not updating by a lot, then also you can stop. Okay. So all these methods of stopping can be useful in some application or other. And these are the 4 methods looking at which you can stop your iterative schemes. Okay. Any doubt till this point before I move forward? Gradient descent is very useful. Like if you apply, if you implement some machine learning model, you will definitely come across a gradient descent method. Okay. Okay. So till now, what I have said is you will have an update condition of form xk plus 1 is x of k minus some alpha times gradient of f at the point xk. This is what your gradient descent method is. Okay. And I also told you when you can stop. Okay. But what I have not told you is how to choose this value of alpha. Okay. So I'll solve one question where I'll explicitly find the value of alpha. But right now, if you talk from perspective of machine learning, you don't want to find the exact value of alpha for which, like, you don't want to look at the exact value of alpha, but you are happy as soon as your loss is decreasing. Okay. So in machine learning application, you treat your alpha as an hyperparameter. Okay. What I mean by that is you take some alpha and see how your model is performing. You suitably increase or decrease the alpha to check whether you are getting a better performance or not. And that's how you tune your alpha rather than finding the exact value of alpha in machine learning application. Okay. So let's say if you take very small alphas, okay, let's say you took your alpha to be 10 to the power minus 2. Okay. So starting from 10, let's say you start from point 10, then you move very less to this point, then you move very less, then you again move very less, and you are taking very tiny step, and you will take too many iterations to reach to the minimum point, right? So you will take too many iterations, right, to reach convergence. Another disadvantage of taking smaller alpha is, let's say your function, like in real life you don't get such clean smooth functions, right? Your function can have a small, let's say, deviation. At this point, let's say your function took this kind of path. Okay. So if you look at this small region, right, I'll try to zoom in. There is a local minima that is forming over here, right? So if you take small steps, you keep taking small steps, if you reach here, you will see that this gradient at this point has become 0 and you will stop, right? So what has happened is you actually didn't reach the global minima, but you got stuck in some local minima. Okay. And which we don't want. We want to reach a global minima. Okay. So from this perspective also, if you take alpha to be too small, it is bad. Okay. Now let's say you took your alpha to be too big. Okay. Let's say you started from this particular point, you took your alpha step, then you again took alpha step. Next time when you took your alpha, you reached here, you missed your local minima. Okay. Then you again came back here, then you again took a step and you again reached here. Now you will again come here, you'll probably go here, and you might miss your local minima. Okay. So the point is, if you take very large alphas, you may miss the target. Okay. Okay. So in machine learning application, you sort of tune this alpha according to your need. Okay. There are methods which actually sort of like Adam, Adagrad. These methods help you choose alpha, but if you don't want to use any of them, the simple thumb rule is, okay, sorry. So the simple thumb rule is, what you do is, you begin with a high alpha. Okay, let's say you initially took alpha is equal to 1. As you go down the iteration, let's say you for first 3-4 iteration, you maintained your alpha to be 1. Then for next 3-4 iteration, you make your alpha to be 0.1. Then for next 3-4 iteration, you again make your alpha 0.01. Okay. Generally, this works. Okay. But again, you might have to tune it according to your need. Okay. So this was second point that I wanted to mention. Okay. Okay. One very small comment that I'm not going to talk about, but I just want to mention so that you have some resources to refer if you need. Just a second. Okay. Okay. So there is something, this phenomena that we discuss about, stucking in local minima, right? This is a very common problem that you encounter uh, uh, with the non-linear models. Okay. So the kind of function that we looked at, this function was convex, it was very smooth, it is a unimodal function, it has all nice properties. But if you look at the surface of loss function of your neural networks, or for that example, logistic regression with some kernels or those kind of things, you will never get these kind of smooth functions. Okay, they will always have a lot of local minimas. Okay, and it is possible that when you are training your loss function, right, it gets stuck in some local minima. Okay, so how would you know it is stuck in a local minima? So you will have high training loss, let's say. Okay, you will have high training loss, and even after applying gradient descent again and again, your loss won't decrease. Okay, your training loss won't decrease. Okay, the reason is that it got stuck in some local minima and it is not able to exit it. Okay, so now I'm going to mention 2-3 methods that people have proposed to overcome this problem of getting stuck in local minima. I'm not going to cover their details. I'm just mentioning it so that if sometime you get stuck like this, you can refer to some of these resources. Okay, first approach is called momentum. So you add some momentum to your gradient descent. This is just what I'm going to say, and you can look at it if you get stuck somewhere. Next method is called AdaGrad, and there is something called Adam optimizer. Okay, so if someday you get stuck in local minima, you can read about these methods, and it can help you get out of that local minima. Okay. Okay. So we have talked about gradient descent. Okay. There are some variants of gradient descent that people actually use. Okay. So you might have heard of something called stochastic gradient descent, or you might have heard something called batch gradient descent. Okay. Now we are going to cover what are these methods. Okay. So different types of gradient descent. Okay. So you remember, if you have a data set, let's say xi comma yi, so you will have many of these data points. Let's say there are n data points. Okay. Then your loss function, let's say j, would be given by summation I is equal to 1 to n, right? And let's say this is a squared loss or whatever loss you want to define. So a loss for regression is given something like this: f of xi minus yi square summation from 1 to n. Okay, somebody asked something. Yeah, RMS prop is also another method. Yeah, that's correct. I think if somebody is really interested in these kind of methods, there is a course on deep learning uh, by Professor Mitesh Khapra. Okay, he's a professor at IIT Madras. Yeah, here he has beautifully explained motivation and everything behind this kind of method. I think he has covered RMS prop also. So you can look at these videos. It's on NPTEL also, and it's available on YouTube also. So you can just have a look if somebody is interested. Okay. Okay. So yeah, what I was talking about is, so your loss function would look something like this. Okay. Now, if you calculate the gradient, right, gradient of j, or let's say, yeah, so this would be, let's say, del j by del a if there are two parameters, or del j by del b, right? Then your del j by del a would look something like summation I is equal to 1 to n, right? Del by, because your derivative splits over a summation, right? You can have different summations. Right. So this is the gradient that you will have, something of this form, right? Summation I is equal to, the second term would be I is equal to 1 to n del by del b f of xi minus yl square, right? This is how your gradient would look like, right? So to make one update in your value of your weights, or make one update in x, by that I mean if you want to do xk is equal to xk minus 1 plus, sorry, just erase it. So if you want to do something like xk is equal to xk minus 1 minus alpha times gradient of j, then you will have to calculate this for all data points, because there is a summation over all data points. So you will have to calculate for all data points just to make one update, which is computationally also not very great. And there are other methods also that, other reasons also that I'll tell you why it's not that great. Okay. So what people have suggested is, why don't you look at a smaller set rather than looking at all the points? Okay. So the first thing that people have proposed is something called, okay, I have written it opposite, but I'll explain it the other way around. So what people have proposed is, rather than looking at the complete data set, why don't you divide your data set, let's say, in 10 parts? Okay. Let's say you divided your data points. So first data point set contains xi, y, I, from I is equal to 1 to m1. Okay. And then the second set contained data points from xi, yi, from m1 plus 1 to some m2. Okay. So what I'm trying to say is, let's say you had 100 training points. You made 10 batches of 10 training points each. Right. Now, in order to calculate the gradient, earlier you were using all 100 points as summation. Now in mini batch gradient or batch gradient descent, mini batch gradient descent, what you will do is, you will just look at 10 points at a time. So let's say you began with x naught, then your x1 is given by x naught minus, okay, so yeah, I'll write it in summation form. So this is some alpha times summation I is equal to 1 to 10. So now you are not summing over all 100 points, but you are just summing over 10 points. F of x, okay, just small change. This is del by del x, right? And then f of xi minus yi square. So in order to calculate your gradient, now you are not looking at all the points, but to make one update, you are just looking at a mini batch. Okay, that's why it is called as a mini batch gradient descent. And it is sort of known, and people have also tried to theoretically show this, that if you use mini batch gradient descent, you have lesser chance to get stuck in local minima. Okay, so you can skip local minima via this method also. The methods that I mentioned above are more sophisticated and more useful, but this also works. Okay. So there is one more method that is called stochastic gradient descent. Okay. So right now we were looking at batches. Now what stochastic gradient descent tells you is that you make batch of only one data points. Okay. So one batch will contain only one data point. So you take some data point, and just based on that data point, you update your x. So you begin with some x naught, x1 is given by x naught minus alpha times. Now you update just using one data point. Okay. So this is called stochastic gradient descent. So you will just update using one data point at a time. Okay. Okay. So this is how you actually implement gradient descent method in machine learning or deep learning methods. And as I said earlier also, gradient descent is the most common method being used to optimize your loss function in machine learning and deep learning literature. So any doubt in this gradient descent thing till now, then we will solve a question from mathematical perspective the way it is taught in this course. Yeah, that is correct. I should have used better notation. Okay, so I can make that correction. So let's say your parameters are theta and you begin with theta naught, right? Then your theta 1 is given something like this. This xi on the right hand side is actually your features, whereas xi on the left hand side I denoted the parameters of your model. I'm sorry for the abuse of notation. Yeah. So this is the parameters that I'm updating, right? And this is your features or your data point. Okay. Okay. Yeah. Okay. So let's look at this example. Okay. So using steepest descent algorithm, the value of function f at the next iteration of unconstrained optimization problem. So we have to minimize this thing, starting with some initial guess this. Okay. So what is the method that is given to us? So x1 we will obtain. How we would be obtain? We would do by x naught minus some alpha times gradient of f at x naught. Right? This is how we will do. Right? So x naught is given to us. First task would be to calculate gradient. Okay. So what is gradient of f? First, so it's a function of two variables, x and y. So partial derivative with respect to x give us 4x minus 3y plus 1. Right? And partial derivative with respect to y gives us uh, minus 3x plus 6y minus 3. Right? So if I have calculated my delta f of fx, right, what actually is my uh, x1? So x1 is x naught minus, so x naught is given to be 1, 1, right, minus some alpha times gradient of f at x naught. So we have calculated the gradient, but we will calculate at this point at 1, comma 1, right? So if I put x to be 1, y to be 1, what do I obtain? 4 minus 3 is 1 plus 1 is 2, right? Then this is minus 3 plus 6 minus 3. This is 0, right? 3 minus 3 minus 3 minus 6 plus 6 is 0. Okay. So x1 I obtain to be 1 minus 2 alpha and 1. Okay. In machine learning implementation, you would have taken this alpha by your choice. But mathematically, we want an alpha so that this x1 minimizes my f of x. Okay. So I want to choose my alpha so that this function gets minimized. Okay. So let's calculate f of x1. This is 2 of x square. So this is 2 times 1 minus 2 alpha square, right? Minus 3, 1 minus 2 alpha, y is 1, plus 3, plus 1 minus 2 alpha, right? Minus 3. Okay, so this 3, 3 gets cancelled. And so what I'm left with is actually 2 times 1 minus 2 alpha square minus 2, 1 minus 2 alpha. Okay. So I want to find alpha such that it minimizes this. Okay. Again, back to our school days, we will do f dash x is equal to 0. So what is f dash x? So yeah, f dash alpha actually to be 0, right? This is a function of alpha now. This is a function of alpha. So this would give us 4, 1 minus 2 alpha multiplied by minus 2, right? Then minus of minus 2 multiplied by minus minus 2 times minus 2, this is equal to 0. Okay. So this thing is given by, this is 4 minus 8 alpha multiplied by minus 2 again, right? Minus plus 4 is equal to 0. So this is minus 8 alpha, sorry, minus 8 plus 16 alpha plus 4 is equal to 0. This gives your alpha to be 1 by 4. Okay. So as you have obtained your alpha to be 1 by 4, you can replace it in x1. So then your x1 is given by 1 minus 2 into 1 by 4, comma 1, which is nothing but, so this is 1 minus 1 by 2, comma 1 is half, comma 1. So this is the next point that you get after one update of your gradient descent method. But again, I'm mentioning that if you use it in application for some machine learning task, you need not worry about optimizing with respect to alpha. So this step can go away and you can choose some good approximation for alpha. Okay. Okay. Okay, I think I can do Newton's method with this, and then we can go above to cover rest of the topics. Okay. So actually what Newton's method is, so I'll try to explain Newton method in briefly. Okay. I'm not sure how much time should I spend on it. Okay, I'll try to explain it completely only. Okay, so that it is useful to you. Okay, so in mathematics, there is a property called intermediate value property. Okay, this is not, I am not sure whether it was done in the lecture or not, but I am planning to do it. Okay, so there is something called intermediate value property. Okay, so what does this property say? Let's say f is some continuous function. First condition is that f is some continuous function. Okay. Right. And some f of a, f is greater than 0. Okay. At some point, you know that your function value f is greater than 0. And you also know that at some point b, it is less than 0. Okay. So what is this says, because your f is a continuous function at some point between a and b. So this is b, let's say this is a, right? At some point C belonging to the set B comma A, right? F of C is equal to 0. Okay. So this is the condition that at some point in this interval, your function will for sure take the value 0. Okay. So there are many methods, okay, which uses this property of intermediate value property to obtain numerical solution to f of x is equal to 0. Okay. So if you are given equation of form f of x is equal to 0, you don't know where you have 0 root. You can look at 2 points where your function on one side is greater than 0, one side is less than 0. Then you would be guaranteed that at some point in between, you will have value to be equal to 0. Okay. So using this intermediate value property, there are few methods. To name a few, it's bisection method. This is not very applicable to machine learning, but because we are dealing with Newton's method, I'll just mention. There is something called secant method. And amongst the most sophisticated one is called Newton method. Okay. They all use this property in different kind of ways. Okay. So if you are interested in this kind of thing, you can just look at it, any numerical analysis book, and you can look at the derivation, how these methods are derived from this property. Okay. The idea is this only, that at some point it is greater than 0, at some point it is less than 0. So we will have a point where it is equal to 0. So how do you reach to this point? That's the whole idea. Okay. Okay. So what does Newton method say is, you start at any point. Okay, let's say you start at point y. If you want to find solution to g of y is equal to 0, okay, so then your next update is given by yk minus g of y divided by g dash of y. If you keep iterating this thing, whatever I have written over here, if you keep iterating this way, your y, okay, let me use some other color, your y will converge to 0 of g. That is, it will converge to a point where g of y is equal to 0. Okay. But how can we use this thing, right, in order to optimize our thing or to find stationary points? Okay, how can we use this thing? Okay. So the way we can use it is, when we want to find the stationary point, okay, how do we find the stationary point? We find the stationary point if f dash x is equal to 0. Okay. So rather than applying this Newton's method on f, if we apply it on f dash x, okay, rather than applying it on f, if we apply it on f dash x, right, we can find a point where f dash x is equal to 0. So that's the idea behind Newton's method. If you talk in terms of optimization, that xk plus 1 is given by xk minus f dash x divided by f double dash x. Now rather than applying on f, we are applying on f dash. So f, this g becomes f dash, and g dash becomes derivative of f dash, that is f double dash x. Okay. So as you know, we are dealing with multivariate functions, so this is similar to writing gradient of fx. Sort of, this is abuse of notation, but I'm using divide over here. Hessian of f of x, right? So this is, because it is divide, it is nothing like, this is like gradient of f of x inverse. So this is Hessian inverse in f, and this is what is our Newton's method. Okay. So Newton's method for optimization is given by xk plus 1 is xk minus Hessian inverse gradient of f of xk. Okay. So what is the advantage of using this method? Earlier, if you remember your gradient descent method, there you had to explicitly choose your alpha. But if you use this method, you don't have to explicitly choose your alpha. This Hessian inverse takes care of that. Okay, so you need not decide upon alpha. You can just keep on applying. Okay. But why don't people apply it in machine learning applications? As I mentioned a few moments ago, that the most common method is gradient descent method. If you have something extra in Newton method, why don't you apply Newton method rather? Okay. The answer is calculating Hessian. Okay. Hessian and inverting matrix Both of them are computationally very expensive. That's the reason why people don't use this method uh, in machine learning applications a lot. Some people might use it for some simpler functions, but generally people don't use it. Okay. Okay. So we have a question on Newton's method. Question is something like, consider the unconstrained optimization problem. Okay. So consider the unconstrained optimization problem. We are given with f of xy. If x1 is the point obtained using next iteration, right? And x naught is given to you. What is x1 minus x naught? So we don't have to do anything much. x1 is given by x naught minus Hessian inverse gradient at this point x naught. Okay. Hessian also you have to calculate it at x naught only. Okay. So this is more of a calculation work. We'll try to do it. Okay. So idea is very similar to gradient descent, but you have to calculate it. Okay. So what is gradient first of all? Gradient of f is given by, first differentiating with respect to x, this is 16x minus 4y, right? Then with respect to y, minus 4y, sorry, minus 4x it would be, minus 4x plus 10y, right? And so what is the gradient at this point? Point is 5 comma 2. So it is 80 minus 16, sorry, 80 minus 8, 4 to the 8, and then it is minus 20 plus 20. Okay, life is easy for us. It's cancelling out. So this is 72 comma 0, right? What is Hessian? You take derivative of this with respect to x, this is 16, right? Minus 4, minus 4, 10, right? So now what you have to do is you will have to calculate the inverse of this matrix, then multiply it with this particular vector, and then you will get your update condition. Okay, so I'll smartly use some tool to invert and multiply. Let's use calculator to invert this matrix and multiply. I don't want to do it by hand, and see what's the answer that we obtain. I'm opening MATLAB. Hopefully it opens soon. Okay, so I'm directly calculating what is my h of f inverse gradient. Okay. Okay, so I'll share my MATLAB screen. Just a second. Entire screen. That should be better. Yeah. So my H matrix is 16 minus 4 minus 4, 10. So H is, I think, no, I am not able to. 16 minus 4 minus 4, 10, right? This is how H looks. And what is my gradient? Grad F is nothing but 72 comma 0, right? So if I do H inverse into grad F, okay, so I made a spelling mistake, so it's grad F now, that's fine. I get 5 comma 2, so this is 5 2, great. So my, x1 is x naught minus 5 2, right? X naught is 5 2, and it's asking me to again do 5 2. So I obtain my x1 to be 0 comma 0, and it is asking what is x1 minus x naught. So this is minus 5 comma minus 2. Okay, now I can just share that screen. Yeah. Okay, so this was about Newton method. We'll talk about penalty method after I talk about constraint optimization. We'll come to this towards the end. And now let's go back to the way the instruction started in that particular course. We'll go to the top. Okay. Okay. We talked about stationary point and those kind of things. So last time we talked about this bifurcation. Yeah, somebody has to say something. Okay. Last time we talked about this bifurcation when we call a optimization problem linear or non-linear. I'll just repeat. So if your optimization problem looks something like this, minimize f of x subject to some gi's less than equal to zeros, then it is called a linear program if all your f and gi's are linear. Okay. If any of them is non-linear, then you call it as non-linear programming problem. Okay. Okay. So there is a special class of problem that is known as quadratic programming problem or QPP. Okay. In that your f of x is quadratic. Okay. But all your constraints, GIs, and all GIs are linear. So this kind of setup is called quadratic programming problem, and it is generally given by minimize C transpose X plus half X transpose QX. Okay. So this is the general setup of your programming problem. Okay. So okay, so next thing that we again discussed last time is when do we call a function as, a program optimization problem as a convex optimization problem. So again, let's say your problem P is given by this. Okay, I can draw some lines like this. Okay. Okay, so if your programming problem is given like something like minimize f of x subject to gi of x is less than equal to 0, and all your f and gi's are convex, then you call this programming problem as convex programming problem. Okay. One small thing that is very important is, let's say if your f is convex, then minus f is concave, right? And vice versa. Because this is the way you define your concave function. You call f as concave if minus f is convex. This is how concave function is defined, right? So one thing is this. Another very small thing is, if you have an optimization problem where you have something like minimize f of x, right? It is same as saying maximize negative of f of x, right? And maximize f of x is same as saying minimize minus f of x, right? So this is what would be used over here. So if you are given a function of form uh, maximize f of x, gi of x is less than equal to 0, then it is same as saying minimize minus f of x subject to gi of x is less than equal to 0. And what you want for this function, this programming problem to be convex, is that you want minus of f of x and all gi's to be convex. Wanting minus f to be convex is same as saying f is concave and all gi's are convex. Okay, and same logic you can use here to say that f and gi are convex. So this would be written as minimize minus of f of x subject to minus of gi x is less than equal to 0. Because I multiplied by a negative sign on both the side, the inequality changes, right? The inequality gets reversed. Okay, that's why you want something like this. Okay. So this is how you can classify whether a problem is concave, convex, sorry, whether a problem is convex or not. Okay. After few minutes, we will see why do we want convexity of our programming problem so much. Okay. Before that, let's solve some questions. Okay. So if you have a quadratic programming problem of the form minimize C transpose X, right, plus half X transpose QX, right, then the Hessian of your, if this is F, this whatever I have written is F, then your Hessian is actually your matrix Q. Okay. This is one thing. Another thing is, let's say if a matrix Q is positive semi-definite, right? Or it is negative semi-definite or those kind of things. Then if you multiply it by some number, let's say half of Q, 1 by 4 of Q, the property will be preserved, right? You should be able to preserve the if you take something common out. As far as this is a positive number. Okay. Now it is asking if you are given a quadratic problem, when can you say that it is a convex problem? Okay. Yesterday, by yesterday I mean in the last session, we talked about how can we say that a function f is convex, right? The easiest way to check was that its Hessian matrix is positive semi-definite, right? So if this is a quadratic programming problem and we want to check whether this is a convex programming problem or not, okay, now your constraints are linear and linear functions are always convex in nature. Okay, so you need not worry about linear constraints. And as I said, in quadratic programming problem, your Q is your Hessian for the complete function. So if Q is positive semi-definite, you are done. Okay. Okay. This is another question. You are given a point. It is asking whether this point is local minima, local maxima, stationary point, not a stationary point. So how do we find out stationary points? Stationary point satisfies is equal to 0. So first of all, let's find out the gradient. Xy, differentiating with respect to x gives y minus 2x minus 2, right? Second one would be x minus 2y minus 2, right? Now we have to check at the point minus 2 comma 2, right? So at minus 2 comma 2, it is 2 plus 4 minus 2. I hope I have not made any mistake. This is y minus 2x minus 2. Yeah, it's correct over here. And y is 2 minus of, this is 4 minus 2. Oh boy. And the next term is minus 2 minus 4 minus 2. So this is not 0, right? So this is actually not a stationary point. I don't know why did I choose this example, but let's look at Did I make some error? Yeah, Gaurav Mishra, you can just unmute and speak.
My question is not related to this particular question you are trying to solve.
Okay.
Actually, I just want to see how we can define a convex quadratic programming problem.
Okay. So you want to know how can
I,
we?
I just want to know the definition of convex quadratic programming problem.
Okay. So if you just look at the name, you are asking about convex quadratic programming, right? So it has two terms in it. First is convex. Next thing that you are asking is quadratic. Okay. So if you have a function, let's consider optimization problem of this form. Minimize f of x, some gi x is less than equal to 0. Okay. So if you want it to be convex, right, the condition is that your f as well as all the gi should be convex. Okay. For quadratic problem, what you want is your f should be of form C transpose x plus half x transpose qx, where q is some symmetric matrix. Okay. I'm going a bit mathematical, but I'll just clarify. Okay. This is your f, and all your gi's, you want them to be linear in nature. Okay. So eventually what I'm saying is your f should be of at most order 2. So something of form x square plus y square plus xy, something like this. F can take up to order 2, up to degree 2, but all your gi's must be linear in nature. Okay. Now what you want to do is you want to merge these two definitions. Okay. So what you want is you want convex plus quadratic. Okay. One thing that you should remember is that if any function is a linear function, then it is also a convex function. Okay. Now, because we have said that our GIs are linear, they are indeed convex also. Okay. So if you talk about convex quadratic problem, right, then what you want to check is whether your f is of quadratic form, right, plus your f is convex. And second thing that you want to check is that all your GIs are linear. Okay. So this is how you can actually define a convex quadratic problem. Okay. And I hope I'm clear.
Yeah, it's very much clear to me. My
Yeah.
just another query related to the same definition.
Mm-hmm.
Suppose that we are talking about a problem where f is quadratic
Mm-hmm.
and it is not convex,
Yeah.
and all the
Yeah.
GIs are linear. All the GIs are linear, but f is not quadratic. It is quadratic, but it is not convex.
Mm-hmm.
It will not be convex quadratic problem in that case.
Then it won't be a convex quadratic problem.
Okay, now another function where the f is quadratic
Mm-hmm.
and your f is a convex function,
F
and
is
the
a convex function.
GIs are not linear.
Okay. But
GIs are
convex.
not linear, but f
Okay.
is quadratic and convex.
So you want your F is quadratic plus convex
Yeah,
and GIs are
yeah,
non-linear.
yeah.
Okay. So
So
then what?
this will also not be quadratic problem.
This
Sorry,
won't be a
convex quadratic
quadratic
problem.
problem. It won't be
No,
quadratic only.
no, for nonlinear constraints, no, we can check the convexity, no, we can just see
No,
the Hershey.
what
Yeah.
I'm saying
So
is,
yeah,
yeah, you can continue. Then I will continue.
no, no, what I mean is, even if the constraints are nonlinear, if it is convex, then the total function will be convex, no?
Yeah.
I'm talking about convex quadratic problem.
Yeah, that's what I'm saying. If you make your constraints to be non-linear, then you can't
Yeah, then
have
it will
quadratic
not be
problem.
quadratic. Then it will not be quadratic
It
in that
won't be
Okay,
case.
okay.
quadratic and hence not
So,
convex quadratic, but
my,
it
my
can still
just
be
just a
convex.
yeah. So my just a request.
Hmm.
Could you please check the question that you have in assignment? That currently we are in, I think week 9, है ना? And in
Yeah.
the week 9, let me just see the question number. because that's why I'm asking this doubt with you. Let's just let my system is getting open. Yeah, I'm asking about the question number 2.
Okay, let me check.
Okay,
Can you
if you can
please
check
repeat
it
that?
whether maybe I'm wrong. I think I'm having some issues that the two options may be correct in that case, because in one option I'm getting a function is quadratic and it is convex, as and the constraints are nonlinear, so that in that case it will not be convex quadratic problem. And another option we have where the functions are not quadratic. Oh, sorry, they are quadratic but not convex, that
So
will also not be non convex quadratic problem. So maybe I'm wrong. I think I'm getting two options correct, so that you can please check if possible.
okay, so what
It
you're
is
saying is in one
VK
of the option your
question number
constraint is
3.
non-linear.
I'm
That's
getting
why.
two options correct, maybe as per the definition. I'll see.
Okay, that is, I think, possible. I'll just have a look at it. Zero. Mhm. One second. So for one of the options, you are getting that this f that you are getting is not convex, right?
Yeah, if you
So
allow
what?
me, I can talk about the options. That's why, because it is
See,
about the assignments, I'm not talking
because
about the which particular option.
that's why I'm also not solving, because we are not allowed to
Yeah,
solve current year's problem.
yeah,
But
yeah, yeah.
I'll definitely
Okay,
post this in
so I'll
discussion forum.
I'll put my question on discussion forum, and I'll put my
The
question on
concerned
discussion
TA who
forum.
checks this assignment, I think
Yeah,
he or she would mark the
yeah. Okay,
both the answers.
thank you. You can continue with yours.
Okay. I can clearly see one of the options have nonlinearity in constraints. So that obviously is not the convex quadratic problem. And it is possible because there are three options, one of them is not convex, so that's why you are getting both these situations. That is very much possible. Okay, so I'll continue with what I was doing. Okay, so this question we were able to do.
The last one, can you we have not completed it. Like, what is the conclusion?
Conclusion was
Third,
that it is
yeah.
not a stationary point because we didn't got gradient at that
Okay,
point
it
in
is
the
not the
space.
stationary point. Okay. And one doubt associated with the same one.
Mm-hmm.
Okay. Suppose for the similar kind of system,
Mm-hmm.
just a minute, let's just take one. When we take the just a- mm, yeah. So once we take the Hessian matrix, it is symmetric, and the first order minors are of different sign,
First order
and
minors are
determinant
of
is
different.
different sign, and the determinant is negative.
Yeah, because they are different sign, determinant would be negative. Yeah. So then your
Okay, then
system
what is the
becomes
kind of
indefinite, right?
high indefinite? What will be what I can say about the point if I
So
evaluate the yeah.
it's a stationary point, right?
Okay. Oh, so I should see del f at that particular point, whether it is zero.
First thing that you should check is del f, right? Then only you should move to Hessian.
Okay. Ah,
And
okay.
after you have said it is a stationary point, then it is neither a local minima nor a
Okay.
local maxima. That kind of
Hmm.
point we call as saddle point, if you remember.
No, can you please repeat? So if del fx is zero, then it is stationary point. Fine. Then
Then it
what
is
is saddle
stationary
point?
point.
A
And if
stationary point.
your Hessian at that point is indefinite, then it is a saddle
Okay.
point. So
Ah. Okay.
you remember this function, this is x cube, right?
Okay.
At
Yeah.
x is equal to 0, it's neither a local minima nor a local maxima.
Yeah.
but if you will look at f dash x, it is 0, and f double dash x is also 0, hence it is not positive semi-definite or negative semi-definite. So it's a saddle point.
Okay, 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 thank you.
Okay, so we have one more question. So the question says, which of the following is not a convex programming problem? Okay, so it's not convex quadratic as we have in this week, but the question is not a convex programming problem. Okay, so in order to check whether it is a convex programming problem, we need to verify both these things, that f and all gi's are convex. Okay, and easiest way to check convex is positive semi-definiteness of our Hessian matrix. Okay, so we can start solving one by one. So for the first example, okay, this is minimum and we are given with a function f. So this actually is a quadratic function. So first let's explicitly calculate the gradient, then we can use a sort of trick to calculate the gradient straight away. Okay, sorry, the Hessian straight away. So gradient over here is 4x, right, plus 8y plus, sorry, what am I doing? This is 4x plus 7, right? And the second term would be 8y plus 6, right? And hence the Hessian would be 4, 0, 0, 6. Okay. So if you look carefully in quadratic function, this term over here is double what you got with x square. Okay. And similarly, this term over here is double of what you had here. So this is 8. I made a mistake in writing here. So this should be 8 because this is 8y. If you differentiate with respect to y, it would be 8. And it's double of what is written over there. Okay. So if you had some xy term, that would have got split over here on the off diagonal. We will see one more example probably where we have xy and then we can verify. Okay. Okay. So this is our Hessian, right? So if you look at its leading principal minus, this is 4, d1 is 4, and d2 is the gradient, sorry, the determinant of this matrix, that is 32 minus 0, that is 0. Both of them are greater than 0, so this matrix is positive definite, which is more than positive semi-definite, and hence your f is at least convex. Okay, now if you look at G, there is only one G. Gradient is given by 2x z minus 2, and Hessian is given by 2, 0, 0, 0, right? And this is also positive semi-definite, and hence first one is convex programming problem. Okay. If you look at the second part, right, here you have a maximization with respect to z, sorry, x and y. Okay, and your constraints are linear. So linear constraint means it is convex. There is a less than equal to sign, so it is okay. Okay. And what do you want this f to be? Because it's a maximization problem, you want your f to be concave. Okay. So if you want f to be concave, it is same as saying you want your minus f to be convex, right? So what is minus of f? It is 6x square plus 4y square. And using the same trick, if you calculate its gradient, it would be twice of this. There is no xy term, so 0, 0, and 8. Again, this is positive semi-definite matrix. Okay. Now let's look at the third part. Okay. Yeah. So let's look at the third part. I'm solving it using this red color. Yeah. So this is minimize. Okay. And if you look at G is very clean. X square plus y square is less than equal to 3. It's a circle, right, of radius 3. Pointed at center, it's a convex function, hence it is a convex set. You can clearly see. Otherwise, even if you look at its Hessian, it would be 2, 0, 0, 2, which is positive semi-definite, and hence G is done. Now, if you look at F, okay, let's try to explicitly calculate for this particular part. So gradient of F is 2x plus 2y, and gradient of F second term would be 2y plus 2x minus 4, right? So Hessian is 2, 2, 2, and 2. Okay. So again, it's just the double, and whatever term you had in 2xy, that thing comes over here. Okay, on the off diagonal matrix. So again, if you look at the principal minors, this is 2, 2 positive. If you take the determinant, this is 0. So again, this is also positive semi-definite, and hence this is also your convex programming problem. Now let's look at the fourth part. I can use blue color to solve this. Okay. So this is maximization. So we want to check for negative. Its constraints are again linear, so we need not check about that. So minus of f is given by minus 3x square plus 5y square and plus xy, right? So its Hessian is given by minus 6, 10, 1, and 1. You can clearly see that the first one is negative. Okay. So d1 is minus 6, and the determinant is minus 60 minus 1 is minus 61. So it is not negative semi-definite, it is the indefinite matrix, right? Because it is indefinite, so this is not a convex function, and hence option 4 is correct, that it is not a convex convex programming problem. Okay. Okay. So let's look at this example. The question is, consider the optimization problem, maximize g of x subject to f of x is less than or equal to 0. Then P is a convex programming problem. Okay, we have discussed this when it is a convex programming problem. So if you don't remember the condition, the easiest way is to reduce it to the general, like the standard form. Minimize something subject to something less than or equal to 0. So if you convert it to that form, it would be minimize minus of gx subject to f of x is less than or equal to 0, right? So what is the condition for this thing being convex? We want minus g of x to be convex, and we want our f of x to be convex. Minus g of x being convex is same as saying g is concave. Okay, and f is convex. So g is concave and f is convex, the correct answer. Okay. Okay. So any doubt before I move ahead? Okay, so very small thing I think you might know, but I just want to mention. In this week's content or in the last week's content, you might have heard a word many times, that is necessary condition and sufficient condition. So like this is a very common way to state any mathematical statement, what are its necessary condition and what are its sufficient condition. Okay, but I'll just try to elaborate what do we mean by this. Okay, so first of all, what is meant by necessary condition? Okay, so I'll talk in terms of stationary point. Let's say I'll talk in terms of minimum point. Okay. Okay. So necessary conditions. Okay. So let's say if x is a minimum point, or if x is a local minima, okay, then list of properties that it satisfies, okay, are called necessary condition. Okay. So what I'm saying is, if x is a local minima, then what are the necessary things that it should satisfy? For example, let's say if you are an Indian, then the necessary condition for you is you live in one of 28 state or 29 state and one of the union territories in India. Okay. Or it is necessary that you speak at least one of the Indian languages, something like that. So if you are an Indian, what are the necessary condition that you must follow? Okay, what are the necessary conditions that comes as an after effect of you being an Indian, or what are the conditions that comes as an after effect of being an minimum point? Okay, so how can these conditions be used? Okay, so these conditions can be used, okay, to deny if a point is not a local minimum, but it can't be used to prove whether, right, it can't be used to prove whether a point is local minima or not. Okay, so if it does not satisfy any of the necessary condition, then you can say that it is not a local minima, because if it was a local minima, then it should have satisfied this condition. So you can deny whether a point is local minima or not, but you can't use it to prove uh, that a point is a local minimum. Okay. The second thing that comes into picture is called sufficient condition. Okay. So second thing is sufficient condition. Like if some of you is from mathematics background, that person must know this, but if some of you is from engineering background, they also generally know, but yeah, I'm just elaborating. So if you satisfy certain condition, right, then x is a local minimum. Okay. So now what it can be used for? It can be used. So what I mean is, so it is a list of condition that if you satisfy, then you can surely say that it is a local minimum. So these are sufficient conditions. Okay. So it can be used to prove a point is local minimum. And what it can't be used for? It can't be used to deny a point. Okay. So it's a sufficient condition. Like if you satisfy these things, then it is a local minima, right? But if it does not satisfy one of these, then you can't say whether it is a local minima or not. So if it does not satisfy one of the condition, then you actually can't say that it is not a local minima. So earlier one you can deny, using necessary condition you can deny, but you can't prove. But using sufficient condition, you can prove, but you can't deny. Okay, I'm thinking of a simple example that I can give you. Uh, Let me just think an example that I can give you to show that both of them are necessary, like important. Okay, probably I can think, and if it comes to my mind, I'll show you. Okay, so if you want to define something, right, then you should give conditions which are both necessary and sufficient. Okay, so that you can use that definition to deny a point as well as to prove whether a point is like a local minima or whatever you want to define. Okay, so in order to define something, you should have that condition should be both necessary as well as sufficient. Okay, now let's come to solving constraint optimization. Okay, so we were dealing with unconstrained optimization till now. Let's say you add some constraints on your optimization. Okay, how do you solve this kind of points? What is the behavior of stationary point and those kind of things? Okay, so the condition or the necessary condition, okay, for a local minima or a local maxima, you can modify it accordingly. So necessary condition for local optimal point are called KKT conditions. Okay, are called KKT conditions. Okay, so if X bar belongs to this feasible region, that is, it satisfies your constraints, okay, then it necessarily satisfies these conditions. First one is gradient of f plus summation of all the gradient multiplied by a factor that is called your Lagrangian multiplier. Okay, these are just terminologies. Okay, so some lambda I multiplied by gradient of gi's. Okay, this should be equal to 0. This is our first condition. Second condition is nothing but it is rewriting all your constraints that imposes a condition that your x dash is actually a feasible point. Okay. Third point is called complementary condition, that your lambda I into gi of xi is equal to 0. What does this actually say is, okay, so if you look at this condition, gi of x is less than equal to 0, when it's equal to 0, we sort of say that it is on boundary of this particular constraint, because let's say you are being asked to draw x square is less than equal to, let's say, 0. Then what you will do? You will first draw x square is equal to 0. X square, yeah, that's not a, okay. So something like x square plus y is x square minus y is less than equal to 0. Then you will first draw y is equal to x square, right? Y is equal to x square. And then you will look at some region, either on this side or on this side, right? So this particular line where you have, okay, so yeah, this particular line where you have y is equal to x square, right? This serves as a boundary, right? So what does this complementary property gives you? This complementary condition gives you is either you are on boundary or the corresponding Lagrangian, when you are not on boundary, then your corresponding Lagrangian multiplier should be 0. Okay. Okay, this is what it gives you. then you are not worried about gradient of that particular constraint. You don't want to add it to 0. Then this term would contribute 0 in the summation. Okay, and you want all your multipliers to be greater than equal to 0. Okay, so these are the set of 4 necessary condition for local optimum. Okay, and what is sufficient condition? Sufficient condition is, okay, so this is necessary plus sufficient condition. So if you take all these necessary condition and you add these 2 points, that f and g are all convex differentiable functions, so these are convex as well as differentiable, then you are guaranteed that your x bar is a local optimal. Okay, so now you might get a hint why we were all checking about convexity and those kind of things, because if your f and g are convex, if it is a convex programming problem, then you can just solve these 4 KKT conditions and obtain your optimal point, which is not the case for non-convex optimization problem. Okay, so let's look at an example. Okay, so this is the programming problem that is given to you. Minimize z subject to this constraint. Okay, if the point this is an optimal point, find the value of alpha. Okay, let's try this. Okay, so first thing that you should check is whether it's a convex problem or not before applying KKT condition. Constraints are linear and hence convex, and if you look at your quadratic problem, it's Hessian matrix is given like 4, 2, -2 and -2, right? So first leading principal minor is 4, second order is 8 -4. This is 4 is greater than 0. So it is a convex optimization problem. Okay. So next thing that you should do is you should apply these KKT conditions. Okay. So let's start with feasibility condition only. So the feasibility condition says that 3x plus 2y should be less than equal to 20, right? So if we start with that, it gives us 3 alpha plus 9 is less than equal to 20. Okay, or it gives us alpha is less than equal to 11 by 3. Okay, so it gives us some information, but it does not tell us the exact value of alpha. Okay, very bad choice of color. Okay, it gives us some value, but it does not give us exact value. Okay, that's fine. So there is only one constraint, so we will have only one lambda. Okay, so let's write the first condition. First condition says gradient of f. So what is gradient of f? Gradient of f is given by 4x. Yeah, somebody has
Just one doubt. Here, should we consider other 2 constraints also? No, minus x less than or equal to 0.
Yeah, exactly.
Or,
Yeah,
yeah, 3 constraints.
yeah,
Okay.
3 constraints. This is minus x is less than equal to 0 and minus y is less than equal to 0. Yes, thank you. Okay, so gradient of f is 4x and then minus 2y minus 5. Okay, and this is 2y minus 2x minus 2, right? And you have to calculate this at point alpha comma 9 by 2. Okay, so this is given by 4 alpha, right, minus 9 by 2 is minus 9, right, minus 5. This is 9 minus 2 alpha minus 2. So this is 4 alpha minus 14, and this is 7 minus 2 alpha. Okay. Okay. So okay. So if you look at the third condition, okay, it says that lambda I, right, gi of gi of x bar is 0, okay, for all I. Now one thing we can see is, like if you look at this constraint minus y is less than equal to 0, right? If you look at the third constraint, then value of this yi that we have is 9 by 2 or minus 9 by 2, and it's definitely not 0. Okay, so lambda 2 would be 0 from here. Okay, and similarly looking at lambda 1, okay, this was for lambda 3, let's name it lambda 3. So lambda 2 times minus of x should be 0. Okay, so either alpha is 0 or lambda 2 is 0. Okay, so this is another condition that we have got. Now let's use the first condition. We have at least obtained that my lambda 3 is 0. Okay, so if now I also have to calculate the gradient of g1. Okay, so this would be 3 and 2, right? This would be 3 and 2. Okay. So now what is my first condition? That sum of all these gradients should be 0. And I can also use lambda 1 times 3 alpha plus 9 minus 20 is equal to 0. Okay, so from here what I can obtain is minus 11 into 0. So either my alpha can be 11 by 3, right? Either I'm hopefully not making mistake. Yeah, I think it's correct. Or my lambda 1 would be 0.
One small doubt. In your del f, no, it is 4 alpha minus 14 and 7 minus 2 alpha. So already it is mentioned it is an optimal solution. No? So we can equate to 0 and find the value of alpha. That's fine.
So you
Your
want
del f
to,
is,
okay, so you want to, what you want to say is, you want to equate this to 0 to find the stationary point.
yeah.
But then,
Because, yeah,
yeah,
okay.
that you can do for unconstrained optimization. If you do it for
Okay.
constraint optimization, then you will have to check the point that you have obtained, whether that lies in the feasible region or not.
Okay.
Yeah, that you can do, but then you will have to do extra checking. Okay. So now let's just try to put it in the first equation and see if we get something. Okay. So this was, okay, let me use this. Okay. So we have gradient of f at this point. So this is 4 alpha minus 14, right? And 7 minus 2 alpha plus lambda 1 times, what is the gradient of this thing? Lambda 1 times 3 comma 2, right? Then lambda 2 times minus 1 comma 0, and we know that lambda 3 is 0. Okay. This we want to be equal to 0. Okay. And we also want that all my lambda I should be greater than equal to 0. Okay. Let's see if we can make something out of here. Let's look at the second row first. This is 7 minus 2 alpha, right? Plus uh, 2 lambda 1 is equal to 0. Okay. So what we can do over here is 11 by 3. Just give me a second. Okay. And another condition that we have is this is 4 alpha minus 14 plus 3 lambda 1. Okay. Can we do something here? Okay, if we just I think we can do something over here. If we just take 2 times of this and add to this, we'll get
Multiply by 2.
yeah 7 lambda 1 minus lambda 3 is equal to 0, or lambda 1 is equal to 1 by 7 times of lambda 3. Okay. And let me just try. And plus 3 lambda 1. And if we use this thing, this is minus 7 lambda 1 is equal to 0. This doesn't give anything extra. So we get set of equation as 7 minus 2 alpha plus 2 lambda 1 is equal to 0, and minus 14 plus 4 alpha plus minus 4 lambda 1 is equal to 0. We want something extra to solve this. Just let me have a look. Just give me a second, I'll check it. I have solved this last week, but yeah, I should have seen the solution today itself. Did I solve this? I was able to make lambda 1 or lambda 2 also equal to 0. How was I able to do that? Okay, let me just see. Okay, so when I solved, I was able to get that my lambda 2 is also equal to 0. Okay, let's say if my lambda 2 is not 0, okay, then what will I have? My x would be 0, right? If my lambda 2 is not 0, then my x would be 0, and what would happen then? Then this term, whatever I have, this term would be non-zero and lambda 1 would be 0, right? So either lambda 1 would be 0 or lambda 2 would be 0. Okay, if my lambda is equal to 0, right? Sorry, what I'm saying is, if, okay, I think I can do it. If lambda 2 is not equal to 0, right? If my lambda 2 is not equal to 0, then my x must be 0, right? If my x becomes 0, x is nothing but alpha, right? Then this alpha becomes 0 and this inner part is minus 11, right? So this would imply that lambda 1 is equal to 0. Okay, and if we just put it in the first condition, what we obtained is this lambda 1 is equal to 1 by 7 times lambda 3. Okay, so these two conditions that is written over here are contradicting in nature. Okay, so the only possibility that we have is that in the first place, whatever I assume that my lambda 2 is not equal to 0 is incorrect, and hence my lambda 2 should be equal to 0. I hope I'm making sense. Because if I assume that my lambda 2 is non-zero and I assume my x is equal to 0, right, then I was able to reach to a point where lambda 1 is equal to 1 by 7 times lambda 3. But I want my lambda 1 to be 0. So both these statements contradict each other, and hence my lambda 2 must be equal to 0. Okay. Now if my lambda 2 becomes equal to 0, then what I can do, then I think we can do, right? Now my lambda 2 has become equal to 0. Any doubt? Please, you can ask. Now I think I can do this. Yeah. So I know my lambda 2 is equal to 0. Then I can just forget about this particular term again. If you have some doubt, you can please unmute and ask. I can forget
No,
about
it's
this.
like, yeah, in the equation, no, just below that, it is
Mm-hmm.
a function of lambda 1 and lambda 2. But after
Mm-hmm.
that, you've written as lambda 3. So maybe with that, it will solve, no? The next two equations,
I'm
that
really
green,
sorry.
yeah,
This should be lambda
yeah,
2 only. Yeah, I keep making these mistakes. Okay. So now I'll have these condition that 7 minus 2 alpha, right? 7 minus 2 alpha plus 2 lambda 1 is equal to 0. Okay. Or, and the next condition is 4 alpha, right? And minus 14 plus 3 lambda 1 is equal to 0. Now you can just multiply it by 2 and add, and you will get 7 lambda 1 is equal to 0, or lambda 1 is equal to 0. You put lambda 1 is equal to 0 in this, then you will get 7 minus 2 alpha is equal to 0, or alpha is equal to 7 by 2. Okay. So the main trick was in showing that my lambda 2 is also equal to 0. Okay. That we did via this path. Okay. So 7 is equal to 2 is the correct answer. Okay. I think we have one more question. Okay, so using KKT condition, the value of beta for which this particular point 1 comma 3 is an optimal solution of the constraint optimization problem. Okay, so we have exceeded the time, but I'll quickly try to do this question. Okay. Okay, as we know the point is 1 comma 3. Okay, then it is clear that lambda 1 is corresponding to x plus 2y less than equal to 2. Okay, so this is x plus 2y minus 2. Lambda 2 is corresponding to minus x. Lambda 3 is corresponding to minus y. Because both the points are non-zero, then my lambda 2 and lambda 3 becomes 0. Right? This thing is pretty clear. Now, just look at the derivative. So what we have is lambda 1 times this x plus 2y minus 2. This should also be equal to 0. Okay. This is one condition that we have. And let's call this f. Then gradient of f is nothing but 4x plus beta y minus 4. And this is 4y plus beta x minus 6. Okay. And evaluated at this particular point, it is nothing but 4 plus 3 beta, right, minus 4. So this is 12 plus beta minus 6. So this is 3 beta and beta plus 6. Okay, this is the gradient. And we can just solve this. This is now gradient of f plus lambda 1 times gradient of g is equal to 0. So if we solve this, we get 3 beta plus 6, right, plus lambda 1 times this is x plus 2y minus 2, so this is 1 comma 2, right? This is equal to 0. So this is 3 beta plus lambda is equal to 0, and beta plus 6 plus 2 lambda 1 is equal to 0. Okay, so let's solve for beta, and we can eliminate this lambda, and that gives us, we multiply this second equation by 3, okay, by 2, sorry, the first equation by 2 and subtract it from the second equation. So this is minus 5 beta plus 6 is equal to 0, or beta is equal to 6 by 5. But there is no option like 6 by 5. Why? Did I make some mistake in calculation? Point 1 comma 3. Oh, just give me a second. I think I might have made some mistake in calculation. So gradient is 4x plus beta y minus 4, that is fine. 4y plus beta x minus 6, right? Yeah. So point is 1 comma 3. So 4 plus 3 beta minus 4, that is fine. This is 4y, so 12 plus 1 beta minus 6. This is correct. Then where is the mistake? Is 1 plus 2y minus 2 is less than equal to 0. So this is 1 comma 2. Okay, I think this option is correct. The answer is correct, beta is equal to 6 by 5. The problem is last time in the last assignment, this point was something else, but just to make it different from that year's question, I changed the point to some arbitrary point. That's why it is not matching this thing. I'll re-verify, and if there is some difference, I'll post in the discussion forum. Okay. Okay, so yeah. If you have any doubt, you can ask. We are already 10 minutes over the time, so I won't start anything new. If you have some doubt, you can please ask. I can just cross check, just stop the recording and cross check if there is